Imagine standing on a street corner as a fire truck races towards you, its siren blaring. The sound is intense, almost overwhelming as it echoes off the buildings around you. As the truck approaches, the siren's pitch sounds higher, more urgent. It's a sound that demands attention, signaling the urgency of the situation. Then, as the truck speeds past and disappears down the street, the siren's pitch noticeably drops. The sound becomes less intense, fading into the distance. This change in pitch, this auditory shift, is not a trick of the mind. It's a real, measurable phenomenon. It's the Doppler effect in action, a fundamental phenomenon that governs how we perceive waves both in sound and light. This effect is crucial in many fields of science and technology. The Doppler effect shapes our everyday experience of sound more than we realize. It influences how we interpret the world around us. Whether it's the changing pitch of a passing car horn, or the altered tone of a train whistle as it rumbles by, these auditory cues provide us with valuable information about the movement of objects around us. They help us understand speed, distance, and direction. But the Doppler effect's reach extends far beyond our terrestrial soundscape. It plays a crucial role in astronomy and the study of the cosmos. It stretches across the vast expanse of space, revealing profound truths about the universe we inhabit. Through the Doppler effect, we can measure the movement of stars and galaxies, unlocking the secrets of the cosmos. The Doppler effect, named after Austrian physicist Christian Doppler, who first described it in 1842, describes the change in frequency of a wave as its source moves relative to an observer. This phenomenon is not only limited to sound waves, but can also be observed in light waves and other types of waves. When a source of waves, like a siren, moves towards an observer, the waves are compressed, leading to a higher observed frequency. This is why a siren sounds higher-pitched as it approaches you. Conversely, when the source moves away, the waves are stretched, resulting in a lower observed frequency. This explains why the siren's pitch drops as it moves away from you. This relationship between frequency, speed, and the observed shift in waves can be expressed mathematically, where f is the observed frequency, which is what the observer actually hears or detects. F is the actual frequency, the true frequency of the source when it is stationary. V is the speed of sound in the medium, which can vary depending on factors like temperature and medium type. Vo is the velocity of the observer relative to the medium, positive if moving towards the source, affecting how the frequency is perceived. Versus is the velocity of the source relative to the medium, positive if moving towards the observer, influencing the compression or stretching of the waves. This equation captures the essence of the Doppler effect, demonstrating how the observed frequency of a wave changes depending on the relative motion between the source and the observer. It is a fundamental concept in physics with applications in various fields from astronomy to medical imaging. The Doppler effect's influence extends beyond the roar of sirens and the rumble of trains. It is a fundamental principle that affects many aspects of our daily lives. It underpins a variety of technologies we rely on every day, from communication devices to medical equipment. One prominent example is the radar speed gun used by law enforcement to track vehicle speeds and ensure road safety. These devices emit radio waves that bounce off moving vehicles, allowing officers to monitor traffic effectively. By measuring the change in frequency of the reflected waves, the radar gun can accurately determine the speed of the vehicle, ensuring compliance with speed limits. In the medical field, the Doppler effect finds crucial application in Doppler ultrasound, a vital diagnostic tool. This non-invasive imaging technique uses sound waves to create images of blood flow through blood vessels, aiding in the diagnosis of various conditions. By analyzing the frequency shifts in the reflected ultrasound waves, doctors can diagnose a range of conditions, from blood clots to heart valve problems, enhancing patient care. These are just a few examples of how the Doppler effect, a seemingly simple concept, has profound implications for technology and our understanding of the world around us, shaping the way we live and interact with our environment. Section 4. Redshift and Blueshift, the Doppler effect in light. The Doppler effect, while initially conceived for sound waves, applies equally to light waves, albeit with a crucial difference. Unlike sound, which requires a medium like air or water to travel, light can travel through the vacuum of space. As a result, the Doppler effect for light depends on the relative velocity between the source of light and the observer, not on their motion relative to a medium. When a source of light like a star moves towards an observer, the light waves are compressed, shifting towards the blue end of the electromagnetic spectrum. This phenomenon is known as blueshift. Conversely, when a star moves away from an observer, its light waves are stretched, shifting towards the red end of the spectrum, a phenomenon called redshift. Section 5. Cosmic Clues, Unraveling the Universe with Redshift. Redshift in particular has revolutionized our understanding of the cosmos. By analyzing the light from distant galaxies, astronomers discovered that the vast majority of galaxies exhibit redshift, indicating that they are moving away from us. This observation forms the cornerstone of the Big Bang theory, the prevailing cosmological model for the universe's origin and evolution. The farther a galaxy is from us, the faster it appears to be receding, a relationship described by Hubble's law. This law, formulated by astronomer Edwin Hubble in the 1920s, provided the first observational evidence for an expanding universe. The redshift of distant galaxies is not merely a consequence of their motion through space. It's a testament to the very fabric of space-time stretching and expanding over cosmic timescales. Section 6. The Expanding Universe, Echoes of the Big Bang. The discovery of redshift and the expanding universe fundamentally altered our perspective on the cosmos and its origins. It suggests that the universe was once much smaller and denser than it is today, originating from an incredibly hot, dense state billions of years ago. The Big Bang. The cosmic microwave background radiation, a faint afterglow of the Big Bang, provides further compelling evidence for this model. This radiation, discovered in 1964, exhibits a uniform redshift, indicating that it originated from a time when the universe was much hotter and denser, consistent with the predictions of the Big Bang theory. Section 7. Conclusion. A universe in motion. The Doppler effect, a seemingly simple concept observed in the changing pitch of a siren, has unlocked profound truths about the universe we inhabit. From radar speed guns to Doppler ultrasound, its applications have revolutionized technology and medicine. Yet its most profound impact lies in its ability to unravel the secrets of the cosmos. Redshift, the stretching of light waves from distant galaxies, provides compelling evidence for an expanding universe, a universe born from the cataclysmic explosion of the Big Bang. As we continue to explore the universe, the Doppler effect will undoubtedly remain an invaluable tool, helping us decipher the symphony of light and motion that shapes the cosmos.